Hello, welcome to our channel for doing statistics using R. In this video, we will talk about how to use exponential distribution in R programming. So we know the exponential distribution is a probability distribution modeling the time between events in a Poisson point process. So the Poisson process is a process in which events occur continuously and independently at a constant average rate. And it is a particular case of the gamma distribution. So gamma distribution is used to model the time between how many times intervals. For example, if you want to know the time until next to occurring of the events. But exponential distribution is to model the time until next single event occurring. So we model this time until next occurring of a constant Poisson event. So the exponential distribution's density function is f(x beta) equals 1 of beta times e minus x divided by beta in power, and x for random time, so x is only possible for positive numbers, and beta is the average or mean time until next event. So the exponential distribution's mean equals beta, and the variance equals beta squared. So in R, if you want to use exponential distribution, you have to use these four functions: dexp for density or probability, pexp for cumulative distribution probability, and qexp for quantile value calculation, and rexp for random number generation. So next, we will show examples in RStudio for exponential distribution. So first, if you want to use dexp function, it will return the corresponding values of the exponential random variable's density. And the syntax for the dexp is for random variable in dexp function, then with a rate. So this rate actually is 1 of beta, which means how many average occurring during a unit time period. So this is the reciprocal of the beta, because beta modeling the average or mean time until next event. So the rate is how many average occurring times in a unit time period. So for example, x dexp is a vector between 1 and 10 with a gap 0.1. Then we can use dexp function to calculate the density of this vector with a rate equals 5. Then we can plot this density curve. So here 1 to 10 with a gap 0.1, so which means here about 100 values. So this horizontal axis represents 100 values, and the y or vertical axis represents the density. So for example, the 20th value, which is about the value is 2. So when the random variable equals 2, you can see very close to 0 for the density. But if here about 0.3, right, 0.3, then the density will be quite high, almost 0.01. And the next function, pexp, will return the corresponding value of the exponential cumulative distribution function. So which means it will calculate the cumulative probability of this random variable. So the syntax is pexp with random variable and with the rate. So we create the same vector for the random variable x, then calculate the cumulative probability using pexp for this vector with the rate equals 5. Then we plot this cumulative curve. So actually this is the cumulative probability for each different values. As you can see for about 2, this value is 2, almost equals 1. And here increase very little, which means the density is very close to 0. But here from 0 to 0.3 increase with the cumulative probability quite fast, which means the density in the previous curve, the density is quite high between this range. The third function called qexp, which will give the possibility to use the qexp function to return the corresponding value of the quantile function from the given cumulative probability. So qexp actually is the opposite operation of the pexp. So for example, we create a vector from 0 to 1 with 0.1 in gap. So this represents the cumulative probability between 0 and 1. Next, we can calculate the q value or quantile value using qexp of this vector of cumulative probability with the rate 5 in this exponential distribution. Okay. Next, we can plot this curve. So this is between 0 and 1. For example, 0.8 probability for the cumulative probability, 0.8. The quantile value is about 0.25 in this exponential distribution. So which means about 80% of the value in this exponential distribution less than or equal to 0.25, right? And the last function called rexp is used to generate a set of random numbers from exponential distribution. So we can use n equals 100, which means we want to generate 100 such random numbers. So we can use rexp 100, then rate 5. Next, we can plot these random numbers in a histogram. So 100 numbers has the count values. So for the lower values, 0 to 0.2 has a quite high count frequency, then lower frequency, very close to 0 in the larger values of random number. Next, we will show an example. Suppose that a system contains a certain type of component whose time in years to failure is given by t. So the random variable t is modeled nicely by the exponential distribution with the mean time to failure beta equals 5. So what is the probability that a component is still functioning at the end of 8 years? So the solution is the probability that a given component has a failure within 8 years is given by px less than 8. So first we calculate the probability of p less than 8 equals pexp 8 then 1 of 5 for the rate. So the probability that a component is still functioning at the end of 8 years is 1 minus the probability of x less than 8. So use 1 minus p less than 8 is about 0.2. So which means in this problem, the probability that a component is still functioning at the end of 8 years is about 0.2 or 20%. You can also download the source files from this GitHub link, and more videos will be uploaded later on YouTube soon. Thanks for watching and subscribing our channel.